So this is, I mean, we could add this to like number 4. And this actually is closest to really showing you how to find the leaves directly. Because if you can find these functions f, so the g's are basically like integrating factors, right? In some sense. And then, well, they're kind of integrating factors. I mean, how to say this? But this much is true. If if you have f equals to a constant, right? If you look at level sets where you have the f sub j is equals to a constant, then those kinds of level sets, the tangent vectors to those will annihilate these. So I think you can read from this the equations for the leaves in the foliation almost directly once you understand this formula. I think it's the, roughly speaking, the generalization of what I did over here with the omega. I mean, with transitioning, the interplay between the omega and the level surface, which defined it. All right, I'm going to shut up.
Wait, so can you explain, right before the line you said theta is equal to df, but then you wrote if d theta is not equal to 0, then theta is not equal to df. What do you mean by that?
All right. I said if, which one?
Well, up there you said theta is equal to df, so theta is exact. And
right.
If d theta is not equal to 0, then theta is not equal to df.
Right, because if theta was equal to df, then d theta would be 0, because it would be d squared.
Oh, okay.
So, I mean...
Oh, so you're just saying,
right.
Then we can make it, so you're essentially using the integrating factor, that's what g is.
I think essentially that's what's going. I mean, this, again, this is a... And you can prove that, I mean, the proof isn't too, it's in Rentlin, actually. The appendix proves that one of these implies that, or vice versa. It's not too bad. It's basically just like differentiating the local slice coordinates or something. But I mean the flat chart. All right. Well, Nathan, we have 7 minutes left for jet space. We should have 12 minutes left. Let me try to at least explain the first example. So it starts with the first order problem. We start with the theorem of Picard. And what Picard says basically is that if you have du dx equals to f of xu, you can solve the initial value problem, which is basically u of x naught. U of x naught equals to u naught, and right. In particular, what I mean by that is you can find u equals to u of x such that du dx is equal to f of x comma u, and u of x naught is equal to u naught. That's what I mean by solve the initial value problem. It's a solution to the differential equation, and it fits this initial condition. Now, the condition that's needed, what's the condition? I mean, Picard's theorem doesn't come for free. You need that partial f partial u is continuous. Maybe you talked about this in differential equations this semester, did you? Do you recognize it? The existence and uniqueness theorem for first order ODEs? That's what this is. Just mentioned it. But yeah, I mean, that's all I do either.
I think we did a couple of check.
Just, oh, yeah. I think that's appropriate for the first course, because to prove this, you have to use contraction mapping, and I don't know, it's somewhat sophisticated analysis to really prove it. So the system then we look at, and I'm not sure this is the optimal thing to look at, but anyway, I'm just following Cartan for Beginners by Thomas and Ivy, just a few things in their first chapter. So they put us to work on this system of PDEs. Partial u partial x equals to a of x y u, and partial u partial y equal to b of x y u. So here a and b are given functions that are appropriate, differentiable, and smooth. Now, if you think about this geometrically, the theorem of Picard basically says that you could think about it in terms of this vector field x. You could think about a vector field x is equal to partial x plus f of x comma u partial u. You could think about that vector field in like xu space, right? And it's it give you some vector field, right? And the ability to solve this differential equation basically is the ability to find an integral curve through that vector field. That's another way of thinking of Picard's theorem. Now, this would then consider, well, what would this define? This would define some plane field. If you think about, so basically think u as z geometrically, okay? So if I pick a point, right, say x naught, y naught, u naught, then if my curve, if I'm stuck with these two conditions, they tell me something about the x derivative and the y. I mean, basically this fixes some little plane there. It fixes a tangent plane like that, given those two conditions. Now, so how do you solve this? Basically, you can solve it by integrating one at a time, right? Use Picard, like fix one of the variables, integrate the other, right? So let's see here. Let me be specific. Set y equals to 0. We'll set y equals to 0, and u of 0, 0 equals to u naught. And then Picard says, what's he say? He says, you can't impose your morality on them. You're not them. You don't have their experience. That's a violation of the prime directive. No, let's see here. Something like that. He shouts at the sky. We can't impose our morality on them. It's a violation of the prime directive. I like the original Star Trek, prime directive. Like, prime directive, whatever. I'll punch you in the face. Stop being idiots and fly to space. Stop being stupid. Like, Then the next generation's like, be stupid. We don't want to tell you what's right or wrong. I mean, yes, we have this existence which is full of peace and no poverty, no hunger, but we don't want to impose that on you. We're beyond that because we're more moral. I don't know. It doesn't seem more moral. But anyway, I don't really believe in peace through space travel anyway, so whatever. But isn't that the Star Trek philosophy? Once you go to space, there will be peace. You peace through what? Peace through the Borg. You're a Democrat. Here. It's like we don't have it. I mean, now I'm getting distracted. I have precious few minutes left. So this gives you a solution that does that, right? And then what do? Then you hold x fixed. You hold x fixed again and use Picard to solve the other one. And you get solution to du dy equals to b of x, y, u with the initial condition u of x 0 equal to u tilde of x. All right. Anyway, all this together, we get u of xy solving 1.6, basically by integrating one and then holding one variable fixed, integrating the other, holding the other variable fixed. Hey, you've been doing this since calculus 3, right? This is essentially the procedure we use to find the potential function from the vector field, right? I don't believe I uttered the words by the existence and uniqueness theorem of ODEs this semester in calculus 3, but I could have. But I have enough sense not to do that. Now, so what's the rub? Basically, these two things are done in isolation, right? This integrates the first one, that integrates the second one, but who's to say that these are consistent, right? What is one thing you can think about that would be a necessity for those to be consistent? What would you need? What relates ux and ui? Right? I mean, we have to have that. So you take those partial derivatives. Now, of course, that's actually what? This is actually ux is what? This is a of x, y, u, partial y, equals partial x of b of x, y, u. Now, by the chain rule, this just gives me a sub y plus a sub u, partial y, is equal to b sub x plus b sub u, partial x. All of these things are at x, y, u. Hey, but what is partial u, partial y, and what is partial u, partial x? Again, we're opposing the differential equations, so ux is, this is b. This is a. So a and b do not exist in isolation. If this is actually going to be an honest to goodness solution, this condition has to be met between the coefficients of this differential equation. Right? This is a so-called hidden equation. This is the compatibility condition, right? Now, so the question is, how do you, if you're given a system of PDEs, right, how can you, discover these hidden equations and somehow impose them in some sort of nice, efficient way, which is even better yet, independent of coordinates? That brings us to what's known as exterior differential systems. What's an exterior differential system? Well, I'm sorry, Nathan, I must admit defeat. But I will make a video, I will post it, I will make up for it. Now, I guess I need to grade you guys. You can hit the. So now I can say all those politically incorrect things I've been. Hey, stop that! I will edit this out. End tape. Scene.